All right. We'll come back on slide you were at it. Start. And all right. So second lecture in logistic regression. Why does it look smaller? Let's see. Announcements. Okay. Lab 9 is due tonight. Homework 7 is due tomorrow. And just a reminder, if you want to attend the experiment with Josh with the mini proctored exam, that's happening today. No, not today, a week from today, 5 to 8 p.m. If you want to attend, please RSVP. We're gonna release some details about the exam soon, so make sure you review those details and then sign up for an exam slot. Okay. 1 second. I think this is still smaller than somehow. Right, this is usually how big it should be, right? See? It's bigger. Just gonna ignore my iPad today. I don't think we're gonna need to write much. Anyways. Okay. So quick recap on what we did last time. We introduced a logistic regression model. So this is a model that makes predictions, right, on the probability that your response is 1, right, given a particular value of your feature. Right? And the way we fit a logistic regression model is by first having a linear regression model and then wrap it around the logit function, right? The sigmoid function. Okay. So we were talking about the loss yesterday, right? We talked about why we can't use L2 loss, right? Well, one of the reasons we can't use L2 loss with logistic regression, right? It's because the loss is not convex. Okay. And because the loss is not convex, your gradient descent is going to be trapped at some local minimums at points, okay? And it's going to affect your estimates of your thetas, okay? So let's talk about another reason why L2 loss might not work for logistic regression, okay? So suppose we have a logistic regression model, and again, right, it outputs the estimated probability of belonging to class 1, right? So what is the largest possible L2 loss for a single data point in logistic regression? What is the biggest L2 loss for just a single data point? Okay. What do we think? You can talk to your neighbors from the wake up exercise. Yeah. All right, seems like the answer stabilized. So what do we think? Okay, majority of the people got the correct answer. So the largest possible error will be what? Why is that? Okay. So let's consider the extremes. Let's actually consider the other extreme first. Consider if your estimated probability exactly matches the true response. Okay, so say the true response is 1, right? So your data point belongs to class 1, and you predict the probability of 1, then your L2 loss is 0, right? Same thing for if your data point belongs to class 0, right? And you predict a probability of 0, you also get an L2 loss of 0. All right, what about the worst case scenario, right? What is the biggest possible error we can make? Well, it could be that the actual outcome is 1, right? The actual response is 1, but the estimated probability is 0, right? So that's the worst thing that could happen, right? You estimate the complete opposite of the truth. Then in this case, your L2 loss is 1, right? Same on the other hand, right? With if your actual response is 0 and your estimated probability is 1, your L2 loss is also 1. Okay. So, and then, right, every other estimate would have an L2 loss that falls between 0 and 1. That's not a very big range, right? Between 0 and 1 for an error, right? You remember in mean square errors in linear regression, our errors can be a lot bigger, right, than between 0 and 1. So that's a rather that's a problem as well, right? Because you really want to have a larger penalty, right, when you're really off. But right now, right, even if you're completely off, the largest error is 1. Right? So if you compute the mean square error, right, over all of your data points, it's not going to get very large. Right? So what do we do with this? How can we do to fix this? Okay? So for logistic regression particularly, we're going to use a loss function that's called the cross-entropy loss. Okay, we're kind of just going to show it to you without offering much motivation here. But if you want to learn about the motivation, they're in the bonus slides in the slide deck. Okay, this is not something that we just magically, pull out of a hat. It has its basis. Okay, but what is a cross-entropy loss? Okay, so some quick notation just to make things simpler. The response for your data points, we will encode it as y, right? So y can be either 0 or 1, and p is your logistic regression model's estimated probability of class 1, right? So kind of standard notation here. Then your cross-entropy loss is defined as the following. It's a piecewise function. Okay, if y is equal to 1, if your true response is 1, then the cross-entropy loss is negative log of p, right? Negative log of the predicted probability of class 1. Again, log in this class and in most classes after this will always refer to natural log. Okay, it's base e. And if your y is 0, if your true response is 0, then the cross-entropy loss is negative log of 1 minus p. So negative log of 1 minus the chance that your data point belongs to class 1. So that's negative log of the chance that your data point belongs to class 0. All right, so let's see what this looks like. Remember what the log curve looks like, okay? So if y is equal to 1, okay, this is what the cross-entropy loss for a single data point will look like, depending on different estimated probabilities, right? It's kind of a curve like this, but look at the labels, right? So for y is 1, you get zero loss when your predicted probability is 1, which is what we want, right? If your true response is 1, we want to predict the probability of a true class of 1. And if you're completely off, right? If your p is 0, right? Or if p approaches 0, right? Because we can't really get there, and p approaches 1, right? So if p approaches 0, right, your cross entropy loss is unbounded here. It's unboundedly large. And same thing, if y is 0, if your true response is 0, you will get 0 loss, right, as your p tends to 0, and you will get infinite loss, right, as your p tends to 1. Okay, so this behavior is ideal, right? Is kind of what we want. And oftentimes you will see the cross entropy loss written not in this piecewise function kind of form, but rather in this format. It's identical to the format on the left. Okay, these define exactly the same function, right? Why is that? Well, think about it, right? If y is equal to 1, then the whole second term, right, on the right, the whole second term disappears. So because 1 minus 1 is 0, right? So the loss becomes negative y log of p. Or negative log of p, right? Because y is 1. And if y is 0, the whole first term goes away, right? Y is 0, right? So the second term becomes negative 1 minus 0, so negative 1 times log of 1 minus p, which is exactly the same as on the left, right? So this is just an easier or a more compact form of the cross entropy loss. Okay? So you don't have to write a piecewise function all the time. Whenever you have something as 1 and 0, you're always going to see something that looks like this written out, because 1s and 0s can easily go back and forth by using that 1 minus. Okay. Anyways, so for a single data point, the cross entropy loss is convex, right? Which is not true for the L2 loss under logistic regression, right? And what about for the whole data set? Right, this is kind of the same idea. We're going to average the cross entropy loss across all of the data points. So just be careful about that minus, right? There is a negative sign, right? That's carried out throughout, right? Because when you take a log of a probability, right? Log of a number that's less than 1, your log of that number is going to be negative, right? So kind of the negative sign outside is going to combat that negative. It's not make it positive. Okay, so this is the cross entropy loss, and now let's combine it with logistic regression, right? So let's plug in our form for the estimated probabilities for under logistic regression, right? You perform a linear regression and you wrap it around the sigmoid function. So this is the form of the cross entropy loss. And your goal, right, is to minimize its loss, right? Your goal is to find the thetas that minimize its loss, right? And those will be the estimates for theta. Okay. Any questions? And lastly, right, we said, right, for individual data points, the cross entropy loss is convex. Right, and now you can see on the right, this is the loss surface for the cross entropy loss over different thetas over the entire data set. And you can see that this is also convex, right? So this empirical risk, right, using cross entropy loss is also a convex function, which is nice. Because gradient descent would guarantee a convergence. Okay. So we have the loss. And now let's kind of analyze the loss and the model and all these kind of together a little bit. Okay, so remember from last lecture, we talked about decision rules, right? So your logistic regression model only outputs predicted probabilities of your data point belongs to class 1, right? It doesn't actually classify this data point into class 1 or class 0, right? It only gives you a probability. And it's your decision, right? It's your choice on how to convert this probability into a class label, a 1 or a 0, right? So this is called a decision rule, right? Again, it's our choice. And the most common and probably the only decision rule that we will use in this class will be just a simple threshold, T, right? And then your predicted probability of 1 is greater than or equal to this T, you predict class 1, and you predict class 0 otherwise. Right? And oftentimes we choose T equals to 0.5, right? So if your predicted probability is greater than half, right, you predict class 1 and 0 otherwise, which is quite intuitive, but you will see later that that's not always going to be the case. Okay, and we talked about linear decision boundaries last time, right? But now let's generalize this idea. So a decision boundary is just a split of your data into different classes based on your feature, right? So for logistic regression particularly, your decision boundary is going to be a hyperplane, right? Last time we saw a line, right? But if you have more than 2 features, it's not going to be a line, right? It's going to be in higher dimensional space. So instead of a line, it's going to be a plane, right? A hyperplane. On the features. So here's what I mean, right? So for example, if I have only one feature, right, the decision boundary that separates the decision boundary that separates my predicted zeros and predicted ones is a single point, right? For example, here, right, the decision boundary is at 0, right? So if this go diff feature is less than 0, I'm predicting 1 class, and then or 0 in this case, I guess. And then if the go diff is greater than 0, I predict the other class, right? So this decision boundary separates my prediction, right? My predicted zeros and predicted ones. If I have 2 features, right? Say go diff, and I guess this is assist from the NBA dataset. My decision boundary under logistic regression is going to be a line, right? So everything above this line, I'm going to predict a class of 0, and everything below this line, I'm going to predict a class. Everything above this line, I'm going to predict a class of 1, and everything below this line, I'm going to predict a class of 0. Okay, and then you can imagine what happens when you have 3 features. Imagine you're plotting points in 3-dimensional space, right? You plot these 3 features in 3-dimensional space, and you will have a plane, right, that cuts through those points. Right, and then everything above that plane, you're going to predict class 1. Everything below that plane, you're going to predict class 0. And remember, we're able to do this because we can convert, right, this threshold on probabilities into a threshold about the log odds, exactly. Okay, but now what I'm going to do is this is all predicted, right? How is this prediction doing? How would it do against the true labels? Okay. So I'm going to plot the same 2 features, go diff and assist on the right. I'm going to plot the same line and the same points. So the only thing I'm going to change on the plot in the next page is the color coding. So I'm going to color code by the actual classes of the points instead of the predicted classes. Okay, so this is what it looks like. It's the same plot. I just color code it differently. Right now, blue means actually, right, this team loses, right? And then orange means this team actually wins. Okay, so you see that our decision rule, right, our decision boundary does not perfectly separate the 2 classes. Right? There are points in the middle, right, that are above the line, but are actually class 0, and there are points below the line that are actually class 1. Oh, you can imagine that in most cases, this is going to happen, right? You're not going to make perfect predictions on every single point, especially for those that are kind of in the middle. Right? But what are the conditions for us to make perfect predictions? Right? One condition that we could, well, yeah, I guess this is a necessary condition, right? That makes the classification perfect is called linear separability, right? So a data set is linearly separable if you can find a hyperplane among the inputs, right, that separates the two classes, right? This is a hyperplane that separates the true classes, right? The actual labels, not your predictions, right? Because, well, your prediction is going to depend on your decision boundary, but this is a plane, right, that separates the two true classes, okay? So for example, right, if we have one feature that looks like this, right, we can separate the two classes for this one feature by finding a point, right, that breaks this data set in half, right? In the, not half, but into parts, right? Into the class 0 part and the class 1 part. So this data set is separable. What is an example of a not separable, non-separable data set? Something like this, right? If it's a little bit hard to see, I have 2 blue points, 2 orange, and a blue here, and then 2 oranges again. Okay, so this blue point is going to cause me some trouble, right? Because I cannot drop a point anywhere and it separates, right? The class 0s and the class 1s. What if I have 2 features? Well, for 2 features, I'm going to look for a line, right, that separates my classes, right? So on the left, there is a line that separates the 2 classes. I believe this is the iris data set from Seaborn. And then on the right, you cannot find a line, right, that separates the 2 classes. I kind of in the middle, there are points kind of mixed up. Okay, so linear separability allows us to make perfect predictions, right? And kind of the intuition on why, right, is that there does exist a line, right, that actually separates the 2 classes. So all you need to do with logistic regression is to find it. Well, this seems like a good thing, right? If you have a linearly separable data set, then your logistic regression model can perfectly predict the classes, right? But in that case, does it actually achieve zero entropy loss? Can it actually achieve zero entropy loss? Okay? Because remember, your loss, your cross entropy loss is 0, right? When you make the prediction that matches exactly as your response. Okay, so here's a question, right? Say we just fit a simple model with one feature and no intercept, right? So there's theta times x, right? So if we fit the logistic regression model like this, what is the theta that will give you 0 loss? If you say train on a data point, x is 1, y is 1. So data point 1, 1. In that case, what is the theta that will give you a 0 loss? That's a Slido question. So take a minute or two. This one does require a little bit of calculation. So talk to your neighbors, kind of try some calculations and see what happens. All right, let's take a look at what people think. Okay, correct answer is infinity, and most of you got it. Okay, so let's see why this is infinity. Okay, so we want zero loss, right? On this point, that's x is 1, y is 1. Okay, so y is 1. When can we, when y is 1, when can we achieve zero cross entropy loss? Well, that's when we predict a probability of 0. Sorry, that's when we predict a probability of 1, right? So we want a predicted probability of 1. That means my logit, right? My output of the sigmoid function has to be equal to 1, right? So this thing has to equal to 1, and I know my x is 1, right? So I plug in x is 1 here, right? So when does this expression equal to 1? Well, the short answer is it never does, right? But if you send theta to infinity, right? You send theta to arbitrarily large, the limit is 1, right? So theta has to tend to infinity, right? In order for your cross entropy to be 1, okay? And then you can imagine, right? If my point is x is 1, y is 0, my theta would have to be negative, tending to negative infinity, in order for my cross entropy loss to be 0. Okay? So is that something good? Can we have an infinite theta? What are we going to do to the infinity? Infinity is not a number, right? We cannot operate on it. Okay. So although it seems linear separability is a good thing, right? Because you can have this perfect separation, under the context of logistic regression, it could be problematic, right? Right? Because your sigmoid curve, right, can never output exactly 0 or 1. Right? So you cannot have a finite optimal theta, right? Your theta, if you want a perfect prediction, has to go to infinity, which is not good, right? So for example, right, if we were to run logistic regression over this data set, which is linearly separable, right? You see these 2 points are very, very separable, right? You can just put a dot here, right? That will separate the 2 points. Well, this is the cross entropy loss over this data set of 2 points. Okay, you see that once your theta goes around 0, then the cross entropy loss kind of plateaus, right? But it's not flat. If you look closer, if you zoom in on, say, Plotly, you'll see that this line has like a very small downward slope. So what you are doing is slowly tending towards 0. Okay, but it's so slow that you just have to keep, right? You have to keep increasing your theta, right, to get a lower and a lower and a lower loss, right? So your gradient descent will never converge under this scenario, right? So that's why linear separability could cause problems, even though it seems like a very good property to have for a data set. Okay, and so how do we avoid this, right? With a linearly separable data set, what do we do so that our theta doesn't blow up? Well, remember, one way, right, to regularize features or regularize the size of your parameters is by regularization. Right? So you can use something like ridge on logistic regression as well, okay? Because ridge will penalize, right, the size of your parameters. Right? So instead of, right, going this slowly downward slope for infinity, right, this is your loss surface for ridge. Okay? Now you have a minimum to tend to, right? And your gradient descent can converge. Okay? this is easily implementable. You can easily implement it in sklearn, right? So for the logistic regression class, there is an argument called penalty, right? So if you put in L2, right, that gives you ridge, and you pass in, right, this lambda. But instead of lambda, what you actually pass into sklearn is the inverse of lambda, right? It's the argument is called C, and that's the inverse of lambda, right? So a large C means a small lambda, a small C means a large lambda. And when lambda is small, that means we have minimal, right? We have, right, kind of weaker regularization. Whereas if lambda is really large, right, we have a very strong regularization. Okay, so here's an example of two logistic regression results run with ridge. One with C equals to 10, so your lambda will be really large. And the other with C equal to 1,000, so your lambda is really small, right? So for the case where your lambda is really large, right, this top case, you see that this curve is quite regularized, right? Your theta is not that big, right? Because a big theta means your kind of increase in the middle is steeper, right? Remember the decimal demo we did last time. Okay, so this is a heavily regularized logistic regression, where at the bottom you see kind of this line, right, perfectly go through these 2 points, right? Some might say it's overfitting, but we only have 2 lines, so we don't really know. But you see that with this kind of minimally regularized model, the increase in the middle is quite steep. All right. Any questions on lambda blowing up to infinity and why that might not be a good? All right, then let's take a quick break. After we return, we'll finish up logistic regression. Okay. All right, let's continue. So you probably saw, right, this if saw this drawing at the bottom right. If you know, we're gonna start using these terms like true positive and true negative things. You will see me confused about these terms, and you might be confused about these terms at some point because they look so similar and they're twisty. Okay. But so what we're going to talk about next is the last step of the modeling process, right? Is now we have fitted a model, right? We can evaluate it, right? So what are some metrics we can use to evaluate a logistic regression model, or more specifically, or more broadly, a classifier? Okay. So you might think the cross-entropy loss itself, right, is the metric that you fit the model over, right? So we can just report that, right? Why is that not sufficient? Why do we need more performance metrics? Well, consider the following scenario where you're analyzing some real estate for a startup, right? The startup sells houses, okay? You build some linear regression model and tell your CEO, okay, we have a really good linear regression model, right? The difference between the predicted and the actual home prices is typically around $10,000. Okay, this $10,000, right, is your RMSE, right? Like this is kind of the interpretation of the RMSE is, right, on average, how far are you off? Okay. The model is trained on the mean square error, so same thing as the RMSE, right? Because it's really just that 1 over n part that's missing, but that's fine, right? Because minimizing the mean square error is the same as minimizing the RMSE, right? So you train a model on the RMSE, and the RMSE is interpretable, right? It has this nice interpretation here, so you can just report it. But what happens when you train a logistic regression model? Well, here's something you might tell your CEO, right? We have a really good logistic regression model. When we predict whether a user clicks on a housing ad, the model has an average cross-entropy loss of 103. What does that mean? I don't know, right? What does the cross-entropy loss of 103 mean? There's no context, right? There's no interpretation, right? So although you fit the model over the cross-entropy loss itself is not interpretable, right? So when you report this, no one's gonna know, right, if this is a big or a small error, right? And how to put this in context. Right? So we need some other metrics that are more interpretable, right, to report. Especially, right, if your predictions are driving some decisions, right? You might be talking to people even outside of the domain, right, of data science, right? People that are, not familiar with these models, right? So we really need these interpretable metrics, right, to build a really convincing story about our analysis. So what are some interpretable metrics for classification? Well, perhaps the most intuitive one is accuracy, right? My classifier's job is to classify points into zeros and ones. So let's just see, right, how many points the classifier actually gets correct, right? So accuracy is a number of points classified correctly over the number of points in your data set, right? So say you have a data set with 100 data points, you correctly classify 75 out of this 100 data points, then your accuracy is 75%. Okay, so straightforward, simple. And it seems like it captures pretty much everything we need about a classifier, right? Classifier with a high accuracy will be something we want, and it's a very interpretable metric. So, right, when things seem simple and straightforward and seems like a free lunch, you have to think if there is a catch to it, right? Sometimes there is no catch, but sometimes there is. So classifier has this problem of being, I guess, overly kind of broad. So consider the following example. So here we're trying to build a classifier that serves as a spam filter for your emails. Right? This is going to be your project B. It's called spam or ham. So you'll classify your emails as spam or not spam, which is ham. Okay. So we encode spam as 1 and not spam as 0. Okay. So suppose you have 100 emails, 5 of them are spam, and 95 of them are real or ham. Okay. So the goal of a email filter, a spam filter, is to actually filter out those 5 spam emails, right? But suppose your friend builds the following classifier, right? This classifier classifies every single email as ham. Okay, so it doesn't matter what the email is, classify as ham. So real email. What is the accuracy of this classifier if you just predict 0 all the time for every single data point? Okay. So let's do another Slido on this. 100 emails, 5 of them are spam, 95 of them are ham, and your classifier predicts ham all the time. Right? It predicts ham throughout the emails, right? Doesn't matter what emails. Ham for all emails. What is the accuracy for this classifier? All right, let's finalize our answers. All right. Okay, let's see what people think. Okay, between 75% and 100%, which is the correct answer. So let's calculate it exactly, right? You can get the exact number. Okay, so if this classifier classifies every email as ham, right? Out of this 100 emails, right, I have 95 hams, right? So I will get those 95 correct, but those 5 that are spam, I will label them incorrectly as ham, right? So I get 95 out of 100 correct. So my accuracy is 95%. Very high accuracy, but is this a good classifier for our purpose? Our purpose is trying to build a spam filter. And this filter, our classifier, has filtered none of the spams, right? This does not detect any of the spams, but you do have a high accuracy, right? But it doesn't do the job that we wanted. What about the other extreme, right? So say another friend builds another filter, right? And this classifier would classify every email as spam. So you'll get those 5 spam emails labeled correctly, and the other 95 you will label incorrect, right? So your accuracy here is 5%. Very low accuracy. However, you detected all 5 spam emails, right? So for the purpose of our classifier, maybe the second one is better, even though it has a lot lower accuracy, right? So accuracy doesn't tell you the whole story, right? In order to, right, build kind of a more holistic, more kind of detailed narrative, we have to dig behind these different types of classifications, okay? Oh, yes. So this is one of the problems with accuracy is when you have these class imbalance, right? You have a lot of classes of, one type and just a few of the other type. Your accuracy could fail in these cases, right? Because you can imagine if you have 50 spam, 50 hem, then, right, both of these classifiers would give you an accuracy of 50%. So it wouldn't kind of have this kind of issue. Okay, so types of classifications, right? So there are really 4 terms associated with types, and then we can kind of combine, right? So here are the terms, right? A positive prediction means you're predicting a 1. A negative prediction means you're predicting a 0. Okay, so positive and negative, they're associated with the actual prediction, with the predictions you make. Okay. And we have true and false. A true prediction means that your prediction is correct, right? So this is about a true response, right? A true prediction means, right, your prediction matches the true response. A false prediction means your prediction is incorrect, okay? So if we combine these 4 terms, we will get 4 more terms, right? Combinations of them. True negatives, false negatives, true positives, and false positives, right? So always, right, the way to read them is kind of backwards, right? Say for true negative, what does this mean? It means, right, negative, it means that your prediction is 0, right? And this prediction is a true prediction. So your prediction is correct, meaning that your true label is also 0, right? So that's what true negative is. Let's do another one, false positive, okay? Positive means that you're predicting a 1, right? A false positive means that your prediction is incorrect. So a false positive means you're predicting a 1, but the true class is 0. Okay, so you always start kind of with the positive and the negative, and then you go backwards. Okay, so now we can divide our classifications into these 4 types, right? And often in practice, right, we will put these the count of these 4 types of classifications into kind of a table or a matrix. This is called a confusion matrix. Okay, and let's pause for a second and think about the numbers in this matrix and what they depend on. Okay, so these 4 numbers in the confusion matrix will depend on the classifier you build, right? If you build 2 different logistic regression models, right, you might have different counts for these 4 types of classification. The data sets you have, right? Of course, right? If you have a different data set, the numbers in this matrix could be different. But one that's important to us is also threshold dependent. Okay, remember what the threshold is, right? That's the threshold where you convert the estimated probability from the logistic regression to the actual class labels that you put, right? So depending on different thresholds, right, you are predicting different numbers of 0s and 1s, right? So that will change the numbers in this confusion matrix as well. Okay, so kind of honing in on this idea of how threshold can change the counts of these numbers in a confusion matrix, let's consider this problem, right? So suppose we have a logistic regression model, right? Suppose we increase the threshold, right? Remember, threshold is the threshold that converts estimated probability to predicted labels, right? So suppose I increase the probability threshold, okay, for my logistic regression model. The model stays the same, okay? The test data I use will be the same as well. What can happen to the number of true positives in the test data? Okay, there might be more than one correct answer. Okay, before we do this problem, let's just practice. What does true positive mean? Positive means your prediction is a 1. True positive means your prediction is correct. So true positive means You're predicting a 1 and a true class label is also 1. Right? That's what true positive is. Okay. All right. So talk to your neighbors. Maybe helpful to write out kind of a small toy data set and play around with the threshold and see what happens. Okay. So take a minute or two. All right, let's finalize our answers. Okay, let's see what people think. Yeah, so 2 right answers could stay the same or it could decrease. Okay, why is that? Let's look at an example. Okay, so I have fitted my model. I fitted my logistic regression model on 3 points. Sorry. Well, I fitted my logistic regression model, and now I have a test set or a validation set with 3 data points, right? And then I output the estimated probabilities of class 1s. Okay, so 0.21, 0.63, and 0.85. And on the second row, I have the actual class labels for these 3 data points. Okay, so let's start with a threshold of 0.3. So when we have a threshold of 0.3, we're going to classify the first point as a 0, right? And the second and the third points as 1s, right? So we have a perfect prediction under this case, in this case, right? So we have 2 true positives, right? For this point and this point, because this is a true negative, right? So we have 2 true positives, so 2. That's a number of true positives. Now let's increase the threshold a little bit. Let's say the threshold gets raised to 0.6. Well, does my prediction change in this case from 0.3? Doesn't, right? I'm still going to classify the first point as a 0 and the second and the third points as 1s, right? So the number of true positives doesn't change in this case, right? So it could stay the same. Let's keep increasing the threshold. Let's say let's increase it to 0.8. What happens here? Well, now I'm going to classify the first 2 points as a 1, as a 0, right? And the last point as a 1. So I have a false negative here, right? So I only have 1 true positive, right? This last point, right? So the number of true positives can also decrease, right? You might think intuitively why this applies, right, to all of the data sets, right? Is as you raise the threshold, it becomes harder to make positive predictions, right? So you just make less of them, right? So the number of true positives will go down or will stay the same or go down. Right? Same thing for false positive, because in general, you're just making less positive predictions. Okay. All right. So we have a couple other metrics that we could talk about now that we have these 4 types of classification. And you will see that these metrics will focus on kind of different things, right? So we'll start with a familiar one with accuracy, right? So this is defined as the number of true positives plus a number of true negatives, right, over the total number of data points, right? Just kind of the same as we talked about before, right? The number of correctly predicted points over the total number of points. The interpretation of this, right, in English is what is the proportion of all points that are correctly classified, right? Or in our spam filter classifier example, right? Accuracy captures the percentage of emails that you classify correctly. Right? So this is straightforward. And we're going to go to some more kind of complicated metrics. So the second metric we introduce is called precision. Okay, so precision is defined as the number of true positive predictions over the total number of positive predictions. Okay, so out of all of the ones you predict are ones, what are the ones, what is the proportion that is correct? Okay, so all of the ones that you predict are ones, how many of them are actually ones, right? For the spam example, what is the percentage of emails that are labeled spam, that are predicted as spam, are actually spam? What percentage of spam predictions are correct? Okay, so that's precision. Okay. The other one that's similar to precision is recall. Okay. Recall is defined to be the number of true positive predictions again over the number of actual ones, actual positive labels. Okay. So out of all of the actual ones, right, the actual positives, what proportion did we detect, right? What proportion did we actually label as positive, right? So for the spam example, what is the percentage of spam emails that we detect? Okay, let's recall. The way you remember precision and recall, right? You can see that they're quite similar, right? So you might confuse them. The way to remember them is just remember one of them. Don't remember both of them. If you know one of them really, really well, the other one you just know, right? Is kind of, you're looking the other way in the confusion matrix, right? So just stick to one, remember really, really well. You're gonna know the other one automatically. Okay. Because these names, I don't think they're intuitive, right? Precision, recall, what are we recalling? I don't know. Okay. And remember, all of these thresholds are dependent. So all of these metrics are dependent on the threshold you choose, right? To convert your probability into class length. Okay. And because they're threshold dependent, we can actually use these metrics to pick our threshold. Okay, more on that in a little bit. But let's go back to our spam example, right? We just said this accuracy could be somewhat of a misleading metric here. What about precision and recall? Well, for the first classifier, where you classify every email as ham, right? So all of your predictions are 0, right? So everything's going to be in this column. Okay. What is the precision, right? Precision, right, is you look at the second column, right? You look at the true positives over the sum of the second column. Right? So it's 0 over 0 plus 0. This is actually undefined here, right? You can't really divide by 0, let alone dividing 0 by 0. Okay. So undefined precision, which is fine. What about recall? So we remember precision is about the second column. Recall is about the second row, right? So true positive over the sum of the second row. Okay. True positive over all of the actual ones, right? So 0 over 0 plus 5, which is 0. Okay, so undefined precision, 0 recall. Probably not a good idea for our purpose, right? What about for our second classifier? Now we classify everything as spam, right? So all the predictions are going to fall into the second column, right? So precision 5/100, right? 0.05, right? This is a very low precision, right? And the reason that it's low, right, is because you have a lot of false positives, right? Remember, these are positive predictions that are wrong, right? So actual zeros you predict as ones. Right? So there are a lot more false positives, so your precision is low, and your recall on the second row is 1, right? So 5/5 plus 0. And the recall is high in this case, right? It's because you have no false negatives, right? Again, precision recall, just remember the properties for one of them, then you remember the other one, right? You can see how kind of twisty this will be in your brain. Like every time I have to use these two, I have to look it up. Like I cannot remember which one is which. So just remember one of them, and then you can recall the other one. Okay. Right. So just like our observations, right? Precision primarily will penalize false positives, right? That's the type of error it penalizes. Recall, on the other hand, penalizes false negatives. Okay. Right. So oftentimes, right, false positives and false negatives are inversely related, right? If you have more false positives, if you have, better way to say it, if you want to lower the number of false positives, then oftentimes you will have to raise the number of false negatives, right? And vice versa. So there's a trade-off going on between these, right? And our kind of goal, right, is to find a balance of these two. But sometimes this balance is not equal, okay? Sometimes false positives and false negatives can come at different costs, right? Our goal is always going to be optimizing the overall cost of both false positives and false negatives, right? We're not looking at just one of them, right? So what is an example that these two types of errors you make could have different costs? So for example, right, we're building a classifier that detects credit card fraud, okay? So in this case, what is a false positive? Well, let's start with false negatives. Okay, what is a false negative in this case? Right, that's when you classify a transaction as not fraud, right, negative, as not fraud, but is actually fraud. That's a pretty big problem, right? You say it's not fraud, but it's actually fraud. What is false positive in this case? False positive is when you classify a transaction as fraud, but it's not. So you're raising false alarms, right? So which one would you rather do? Missing more actual frauds or raising more false alarms, right? In this example, right, false negatives, right, missing these fraud detections is a lot more costly than just raising more false alarms, right? So in this case, the cost of these two types of errors are not the same, right? So in this case, it's okay, right, to have a low precision, right? So to have a lot of false positives, as long as we have a high recall, right? As long as we detect all of the fraud, right? As long as we have a very low false negative. Can you imagine this is the same thing with, say, disease detection, right? You would rather say, right, someone has a disease and, you know, send them to more tests and more examinations than saying they're okay and they actually have the disease. Right? So in many cases, we would want to have, you know, a higher recall than low precision. You can think of examples for the other case. When would we want a high precision and a low recall? All right. So, like I said, right, the precision and recall, they both depend on the thresholds you choose, right? So we can actually use precision and recall to help us pick a threshold. Okay, here's how we're gonna do it. Okay, so we have some training data. We're gonna fit our model to our training data. We're gonna estimate right, generate these estimated probabilities, right, for our validation data. Okay, so we did a train validation split here. Okay, so estimate probabilities for the validation data. So you have a bunch of probabilities. Then what you do is you convert these probabilities into predicted classes using a bunch of different thresholds. Okay, say here, right, I have 99 thresholds. So I just have 99 sets of predicted labels. And then on each set, I can compute these performance metrics like accuracy, precision, recall, right? They're all dependent on the threshold. Okay? And we can plot these metrics. So for example, here what I'm doing is with a data set, you can look at a data set and a code in a demo. I'm plotting the threshold against the accuracy. And you see that at threshold around 48%, 0.48, I have the highest accuracy. So in this case, right, the best threshold in the accuracy sense is not exactly a half. Okay. All right. So, and you know, as you raise or decrease your threshold, your accuracy will drop. But right now that we know the underlying 4 types of classification, you can tell, right, why the accuracy is dropping, right? When you raise your threshold, you're gonna have a lot more negative predictions, right? You'll predict a lot more negatives, right? So you're more prone to having false negatives. Whereas if you lower your threshold, right, then you're gonna have a lot more predicted ones, right? So you're more prone to false positives. Okay. You can also plot precision and recall. These are often plotted together in what is called a precision recall curve, right? So you just basically plot both metrics against the threshold. Also, we often just plot precision and recall with different thresholds together, right? So dropping the threshold, just look at precision versus recall. And then we find a place, right, where both precision and recall are high, right, are relatively high. Okay. But again, right, this depends on, does the false positive and the false negative have the same similar cost, right? So sometimes you might not want to balance precision recall. Sometimes you might want one over the other, right? But if you do have similar costs for these 2 types of errors, what you can use to balance precision recall is called the F1 score. Okay, F1 score is defined to be 2 over 1 plus 1 over precision plus 1 over recall. This is a harmonic mean, okay, of precision and recall for the F1 score. And our goal, right, is to find the precision and recall, is to find the threshold that maximizes this F1 score. Okay. You often use when there is a large class imbalance. Okay. Like our spam and ham example. And we just pick the threshold that maximizes F1 in this case. Again, depending on if you have similar costs for the 2 errors you can make. All right. So here's an example of how we maximize, right, the F1 score. So here I plot the threshold against F1. I find the threshold, right, that maximizes F1, and on my precision recall curve, this corresponds to about this point right here. Okay. All right. 2 other metrics. So before, right, we looked at a column and a row, right? Precision, recall. Now we're going to look at 2 rows. So we're looking at the actual zeros and the actual ones. So the first metric is called the false positive rate. Very, very confusing term. Why? Because it operates on the actual negatives, the actual zeros. Okay, so out of all of the actual zeros, how many do we classify incorrect? Okay, false positive means that you're predicting 1 but the actual 0, right? So out of all the actual zeros, how many do we classify incorrectly? And another metric is called a true positive rate. This is the same as recall. Okay, so out of all of the actual ones, right? How many do we classify correct? Okay, we have kind of a memory tip at the bottom to memorize these. Again, these terms are, you just have to work with them a lot to be able to remember which one is which. Okay, so false positive and true positive. What we can do, right, with these two is to plot them together. Okay. And this will help us pick a threshold as well. Okay? So plotting false positive rate and true positive rate of different thresholds together is called plotting a ROC curve. ROC stands for receiver operating characteristic. It's a kind of a radar term from World War II. Okay, false positive rate versus true positive rate. And how do we pick a threshold over this? Which point, right? Which threshold do we pick based on this curve? Okay. Well, if you look on the top right corner, right, here is when you have a low threshold, right? Because you have a lot higher false positive rate and true positive rate, right? Because you're making a lot more positive predictions when your threshold is low. If you look at the bottom of this curve, right, this is when the threshold is high, right? You make more negative predictions, right? So both true positive and false positive will be low. Right? So how do we pick a threshold based on this ROC curve? We have to compare it against the best classifier we can get. If we have a perfect predictor, right, this blue curve, or it's not even a curve, right, just kind of a two lines, right? This blue curve represents the ROC curve for a perfect predictor. Okay. And if our classifier behaves randomly, so every time it has to classify, it flips a coin. This is what its this green line is what its ROC curve looks like. Okay. And we just compare the ROC curve of our classifier to these two extremes by looking at the area underneath it. Right. So the perfect predictor is going to have an area under this ROC curve as of 1, right? This is called the AUC ROC, area under the ROC. Kind of awkward to say, but right, the perfect predictor is going to have a AUC ROC of 1, right? And this random predictor, right, this flip of a coin predictor is going to have an AUC of 0.5. Right? So our goal would be building a classifier, right? So this is less about threshold, I guess, right? More about your actual classifier. It's building a classifier that gives you a large AUC. Okay. All right. I think that should be everything I want to cover. Okay. Okay, one last thing about ROC curve, I guess, right? So we talk about, right, our ideal classifier is one that aims to maximize the AUC, right? The area under this ROC curve. Right? What about the threshold? How do we pick a threshold? Well, here, right, true positive is a good thing, right? False positive is not a good thing, right? So we want to pick a threshold that will maximize true positive while minimizing false positive, right? So on this curve will be, I guess, somewhere around here, right? Because if you go lower, then your true positive rate will drop, but if you go higher, your false positive rate increase, right? So probably somewhere around here, but is subject to experimentation. Okay, so this ROC curve does two things, right? It does help you find a threshold, but also if you look at the area underneath it, it helps you kind of evaluate the performance of your classifier. Okay, so that's pretty much all I want to talk about logistic regression and classifiers. You're gonna work with these metrics we talked about today a lot in your homework, lab, and your project. So don't worry if these terms seems a lot to digest. But just remember, right? Precision recall, stick to one of them, right? And remember one of them, you're gonna remember. Okay. All right, I will see you on Monday.